Hello, welcome to a new tutorial presented by the SHRLB on electronic structure. The reference is Cambridge International AS Chemistry by Laurie Ryan and Roger Norris. Welcome to this tutorial on electrons in atoms. So in this the learning outcome is going to be describe the number and relative energy of sp and d orbital for principal quantum number 1, 2, 3 and all this. So describe the shape of sp orbital, state the electronic configuration of atom and ions given the proton number and charge using the convention 1s2 2s2 p6 and etc. And now we have explained and used the term ionization energy and the factor influencing the ionization energy of element. Use the ionization energy data to explain the trend across the periodic table and down the group of periodic tables. Deduce the electronic configuration of elements. Interpret successive ionization energy data of an element in terms of position of that element within the periodic table. Okay, so these are the different learning outcomes. Before we start this different learning outcome, I want to brief you on the introduction of the electronic shell. So the point number one is that electronic shells, according to the Bohr model, was actually vague. According to the Bohr model, we only considered one of the electronic shell factor, which was being called the principal quantum number. And now we need to know that another method of considering electronic shell is via the Schrodinger model. So in the Schrodinger model, we need to know that Schrodinger came up with an equation, and this equation was called the Schrodinger equation, where he had the partial derivative of the different components of the shell number in the different direction x, y, and z plane. Why in Bohr, you see that Bohr only considered in the atom existing on a plane surface, while Schrodinger considered an atom existing in space, in a three-dimensional space. So these are two different views. So now, in that differential equation that Schrodinger had, he had different solutions. The first solution was called the principal quantum number. The second solution was called the azimuthal quantum number. The third solution was called the spin quantum number, and the fourth solution was called the magnetic quantum number. So point number one, principal quantum number. The principal quantum number is represented n, and this n shows the energy that each shell contains. So example, 1, when n is equals to 1, n is equals to 1 has a lower energy compared to n is equals to 2. And when n is equals to 2, it has a lower energy compared to n equals to 3. And when n is equals to 3, it has a lower energy compared to n equals to 4. That is the whole of the principal quantum number. The next point to put in your mind is the azimuthal quantum number. This factor or this solution is used in order to show the shape of the atom. So we have different number corresponding to azimuthal quantum number. So the first number is 0. 0 is showing that it is S subshell. So when you have a 0 azimuthal quantum number, it means that you have an S subshell. And S subshell is actually spherical in shape. So when you have S subshell, it's actually spherical in shape. The second number is 1. 1 shows that you have one shows that you instead have a one shows that you have a dumbbell shape and is represented as P. So 1 shows that you have a dumbbell shape and is represented as P, and the next one is 2. 2 is showing the D configuration. The D configuration has 10 electrons. So now, in order for you to have this number of subshells which are existing in the different azimuthal quantum number, we need to use a certain formula, and that formula is n squared minus 1. So example, I initially told you that azimuthal quantum number could be starting from 0 to n. So we have 0, 1, 2, 3, 4, 5, 6, and etc. So example, so this the spin quantum number the first one is the S subshell. So for this S subshell, we need to just know that there exists only one for the S subshell, there exists only one subshell. That is for S. So that's for zeros. Now for 1, when you do 1 squared, so actually it's going to be actually n squared plus 1 instead. N squared plus 1 to have the different subshells. So we start by doing in the case of the S. For S, you see that the azimuthal quantum number L is equals to 0. So L squared is going to give you 0 plus 1 is going to give you 1. So you are going to have one subshell inside and azimuthal quantum number. In case where you have azimuthal quantum number of 1, which is a p subshell, you have 1 squared, which is 1 plus 1 squared is equals to 1 plus 1 is going to give you. So this is a different point to note here. So, and now the next one is the magnetic quantum number, and the magnetic quantum number is there in order to find the geometry, how the different shells are going to orient in space. And lastly, you have the spin quantum number, which is going to show that each electron is going to spin in an opposite direction in one shell. That is, this number are represented as negative half and half. So these are the points to note here. So let's start. So the simple electronic structure according to the Bohr model, we need to know that lithium only has one electron. So for the simple electronic structure, you need to know that the shell 1, that shell 1 is actually the principal quantum number 1. Is going to contain 2 electrons. Shell 2 is a principal quantum number 2, is going to contain 8 electrons. When you have 2s, 2p, and 2s and 2p, so 2s is going to contain 2 electrons, and then 2p is going to contain 6 electrons. So it's going to make a total of 8 electrons. For the principal quantum number 3 is going to contain 2s. You are going to have 3s, 3p, and 3d. 3s contain 2 electrons, 3p contains 6 electrons, that makes 8, and 3d contain 10 electrons, so that makes a total of 30 of 18, and that's the same as 4s. 4s, for 10 electrons. So these are the points to put in mind in order for you to have the different number of electrons. So now, evidence of electronic structure. So evidence of electronic structure. Ionization energy, we need to know that. So this is the evidence now that you have different subshells in a particular shell. So this evidence is going to be shown by an ionization energy, and the ionization energy is the first ionization energy is being defined as of an element, being defined as the energy needed to remove one electron from each atom in 1 mole of atom of the element in gaseous state to form 1 mole of gaseous unipositive ions. So these are the points to note. So on this electronic structure, you can see that it's going to produce both. You can use this electronic structure, this first ionization energy, seen both in an absorption spectra here and emission spectra, which are being seen below here. So these are the different spectra that you can visualize. So now these are the different electronic structure, and now when visualizing this experiment or evidence for electronic structure according to these different mass absorption or emission spectra, we can now see now the 3 factors which influence the ionization energy. There are 3 main factors which influence ionization energy. The first one is the size of the nuclear charge. We need to know that the higher the positivity of the nucleus, that is, the more there are protons inside the nucleus, the more the electropositive or the electronuclear attraction, the more the electronuclear attraction. The next point is also the distance from the outer electron from the nucleus. The greater the distance from outer electron to the nucleus, the lower the electronuclear attraction, and thus you are going to see that the ionization energy is going to reduce. Here the ionization energy is going to increase because more energy is going to be required to pull the electron outward. And now the last is going to be shielding effect of the inner electron. You need to know that the more there are inner electrons which are separating the outer electron from the nucleus, the greater that shielding effect. Those electrons are going to cause repulsion to the outer electron, and that repulsion is going to be called shielding effect. So full inner shell electron prevent the full nuclear charge from being felt by the outer electron. That's being called shielding effect. And when it prevents as such, it's going to cause now the first ionization energy to decrease. So this is why you can visualize it as such. We see that this is across the same period. So let's visualize what happens. So number of electrons being removed, you see that for this is one atom. So what is going to happen? You see that when you remove the first electron in one atom, the ionization energy, let's say that this atom is a group 1 element like sodium. So this is actually sodium. So when you remove the first atom, you see that ionization energy is actually very small because of that shielding effect of the inner 8 electrons in sodium. So that first outermost electron, this is actually how sodium resembles. So we have 1 electron outside, we have 8 electrons inside here, and then we have 2 electrons in the innermost shell. So these 8 electrons are going to shield the outer electron and the outer electron here, and this distance also is going to be quite long. This is going to cause you the first ionization energy to be very small compared to the second. So in the second ionization energy, you enter now the next, so distance is smaller, and now the distance is smaller, and now the shielding effect is reduced. So in this case, you have shielding effect is reduced. So you see that since the distance is smaller and shielding effect is reduced, you are going to have an increase in ionization energy. So now this increase in you are going to have a small increase in ionization energy here, just because of extra stabilization of the atom. This small increase in ionization energy here, so is more difficult because of extra stabilization. As you can see here, the second electron is much more difficult to remove than the first. There is a big jump value of ionization. This suggests that the second electron shell is closer to the nucleus than the first. Taken together, the first and second ionization energy suggests that the sodium has 1 electron in outer shell. Then the next one, we have from the second to the ninth electron remove, there is a gradual successive increase. This suggests that all the 8 are in the same shell. So all these are in the same shell because it's a gradual increase, and that gradual increase is because of extra stabilization. The more you remove one, the more it's stabilized to reduce, to increase the energy that is going to be reduced. And now you have again a great jump to this position because you are entering another shell and to remove now these other ones. So these are the points to put in mind. And now the next point you need to know, as I've initially told you, I've told you about the azimuthal quantum number. The azimuthal quantum number are what are going to have the representation S, S, SP, SPD, and all this. So this is the azimuthal quantum number. In order for you to have we need to know that what the 1s is actually going to be the smallest energy. Then you have at n is equals to 2, you have 2s and you have 2p. At n is equals to 3, you have 3s, you have 3p, and you have 3d. So n is equals to you have only one subshell. When n is equals to 1, you only have one subshell. When n is equals to 2, you have 2 main subshells. You have 2 main subshells, but you need to know that this p have again 3 subshells on it. So you have 4 subshells at n is equals to 2. At n is equals to 1, you have 1 subshell. So this is represented as n squared. So at n is equals to 1, you have 1 subshell. 1 squared gives you 1. At n is equals to 2, you have 4 subshells. So you have 1 subshell for when you have azimuthal quantum number S, and you have 3 when it is P. At n is equals to 3, you have 3 squared, which is 9 subshells. At n is equals to 3, you have inside you have 3 squared, which is equals to 9. So you are going to have so 3 squared gives you 9. You are going to have 1 from the S, 3 from the P, and 5 from the D. And we have again this other one. In order to have the different subshell of S, you need to know that S is always 1 subshell. Then P, you add plus 2, is going to give you 3. Then D, you add plus 2 again, going to give you 5. Then F is plus 2, then it's going to give you 7. This is how you have the different subshell of the different azimuthal quantum numbers. So now these are the different points to put in mind. So in order for you to see this energy, in order to have this representation of energy, you need to follow this diagram. 1s first start to go to 2s, then it goes to 2p as well, then it goes back to 3s, then it goes to 3p, then it goes to 4s, then it goes back like that, then you have 4p as such. So these are all the different points in order to have the format of electronic configuration. So from this diagram, we see that the 4s has a lower energy compared to the 3d, and the 4d has a lower energy, has a 5s has a lower energy compared to the 4d. So these are the points to put in mind. And in order to see that, you are going to use this arrow diagram. So now let's see some electronic configurations. So hydrogen is going to be 1s1. So helium is going to be 1s2. When you fill the s, the first 1s, you now fill now the 2s. So we are going to have lithium is going to be 2s1, beryllium is going to be 2s2, boron is going to be 2s 2p. Then that you just continue by number until you have 6 electrons on the p, because each subshell at the p is going to contain 2 electrons. So that's the point to note. I've initially told you that an S subshell is going to contain 1 subshell, a P subshell is going to contain 3 subshell, a D subshell contains 5 subshell, and each subshell is going to contain 2 electrons, which are going to move in opposite direction controlled by the spin quantum number. So you are going to have a total of 2 electrons in a 2s subshell. You have a total of 2 electrons in the S subshell. You have a total of 6 electrons in the P subshell, and you have a total of 10 electrons in the D subshell. Also have a total of 14 electrons in the F subshell. So these are the points to put in your mind. So you are going to have total, you're going to increase to 2p6, and then to 3s1 you are going to have an increase as such here. So now we have the progression. Let's see the progression of first ionization energy according to periodic table. So we see that from hydrogen to helium, we see that there is a drastic increase in first ionization energy, and the reason is because from hydrogen to helium, so there is a general increase across the period. So as you move across the period, you have an increase in first ionization energy. So from hydrogen to helium, and period 2 to from lithium to neon, and also to other periods. As you go across the period, the nuclear charge, you see that from hydrogen to helium, the nuclear charge increases, and since the nuclear charge increases, the electronuclear attraction is going to increase, which is going to cause the increase in first ionization energy. That's the first point. Now you see that there's a rapid decrease when you move from the helium to lithium, and this rapid decrease is because of the shielding effect. We need to know that the third electron, which is inside lithium, is inside the 2s orbital. It is no more inside the 1s orbital. So you see that the shielding effect is going to be shielding effect by the 1s electrons from the interaction of those electrons to with the proton inside. So that's why lithium has a lower energy. And now we see that there is going to be increase to beryllium here, because the second electron, the third electron which enter inside the next electron will enter inside beryllium is going to enter into the same shell, but you have an increase in electronuclear interaction. Since you have an increased electronuclear interaction, but the distance is kept constant and the shielding is not increased, you are going to realize that the ionization energy is going to increase. The next point is going to be boron. You see that boron have a slight decrease. You have a slight decrease, though there is an increase in electronuclear attraction. So though there is an increase in electronuclear attraction due to increased number of proton, boron has a lower first ionization energy compared to beryllium, and this reason is because the partially full electron are much more stable compared to partially full electron are more stable compared to completely full. So in case we see that there is a slight decrease from beryllium to boron, because on the removal of one electron, you note that beryllium has 1s2 2s2, so it's stable, while the boron has the 1s2 2s2 2p6 2p1. So this electron in the 2p is less stable compared to this form, so it's going to easily come out as compared to in case of beryllium. This is why the ionization energy is going to be lesser in case of boron than in case of beryllium. So these are the points to put in mind. So now the next point is there is also a slight decrease from nitrogen to oxygen, and this is because we need to know the electronic configuration of nitrogen and that of oxygen. For nitrogen, electronic configuration is 1s2 2s2 2p3, and oxygen is 1s2 2s2 2p4. I've initially told you that a completely full subshell is more stable compared to a partially full subshell, and a partially full subshell is more stable again compared to a non-full subshell. So now this non-full, so this is a partially full subshell here for nitrogen, this is a non-full subshell. So now we see that in case of nitrogen is partially full, and then it's going to be much more, the electrons here are going to be much more stable than in a complete not full subshell. So this is a not full subshell. So in this case it is not going to be as stable as in this case where it's partially full. So now when you have the so it's completely full is is more stable compared to a half full, and a half full is more stable compared to the partially full. So now comparing this, you see that this one is going to be less stable, is going to be more stable compared to this one, and then you are going to visualize that electron is going to easily move out in this case than in this case. So this is what we visualize in this tutorial. I say thanks for your kind attention. Please don't forget to like and subscribe for this channel. Thank you.